last day properties of waves are interference. Interference so we start from speed of sound in the air part like so we start from diffraction. This diffraction starts from so properties they are together, right? But interference you right, reflection you right, diffraction you right. Diffraction. So diffraction is right. So diffraction is a phenomena when a wave hits an obstacle or barrier, right? It bends. Like suppose this is an obstacle, here's the wave comes. You're transferring a different wave vector, right? When a wave reaches or strikes on a barrier or some obstacle, it bends. Right? It bends like this. It bends and spreads. Close like this. Right? These are the wave fronts, and this is the direction of the wave travels. When the wave front passes barrier at the edge of it, it gets spread. The spread wave. So this phenomenon is known as diffraction. And also, not only from a barrier, whenever there is a aperture or small hole, when a wave goes through a narrow aperture or hole, it spread out. It goes like this. The wave runs spread out. So this phenomenon is known as diffraction. Wave එකක් මේ වගේ narrow aperture එකක් නැත්නම් hole එකක් තියෙන තැනකින් යනකොට එහෙම නැත්නම් මේ වගේ obstacle එකක් තියෙන එකට edge එකකින් යනකොට edge එකකින් යදි bend වෙනවා. bend වෙනවා පිට යනවා. right? එහෙම නැත්නම් මේ වගේ narrow hole එකක් තියෙනකොට spread out. Right? So this phenomenon is known as diffraction. Right? So in order to observe, pronounce diffraction, right? So the condition is, there's a condition that this wave should satisfy. Suppose the size of this aperture, size of this obstacle or this hole is equal to A, the width of the hole. And also the wavelength of the wave is lambda. So we can observe this diffraction of wave significantly if the size of this hole or obstacle is less than the wavelength of the wave. If the lambda is greater than the size of the aperture or size of the obstacle, you can observe diffraction very well. Right? So you can see diffraction very well. Right? So we can demonstrate that. Right? Suppose now we are widening this gap between the two plates like this, keeping the wavelengths similar. We are widening the gap. So what will happen? Wavelength is similar or same. What can you see? Diffraction. What will happen to diffraction? You can see diffraction is this wave get very diffraction or not? Right? This goes like this. The spreading thing is now less. less spreading. Diffraction is now small, right? Diffraction එක වැඩි වෙන්නේ නැහැ ඒක. Spread වෙන්නේ නැහැ wave. Here the wave has spread out very well. Now in this case, spreading of wave is very actually this spreading is within a very narrow region, right? So the diffraction is not very well here. What happens when the gap between these two obstacles are very large? Hole is very large because they are what happens to diffraction? The A is very, very large than lambda, right? Minimum diffraction weighted now, right? So the wave from this aperture is like this. No diffraction you can see, right? And also remember, wavelength does not change. Wavelength is the same. It keeps the same wavelength. You not seeing it. Okay. So due to the diffraction of sound waves, what you can hear? Diffraction of sound waves. Sound waves can get diffract from something like this, the space where light, space, it can be diffract from a larger gap, right? But light can't get diffract from this size of gap because the wavelength of light is very small, right? There will be sound wave method diffraction එක අපිට observe කරන්න පුළුවන්. ඒගොල්ලෝ මෙතන ඉඳින්න කතා කරනවා නම් we can do that. Right? මේ අයින්ට කියද්දී ඒක හොඳ නැහැ කතා කරනවා. Right? Sound wave with waves and yes. Very right. Yeah. ඒගොල්ලෝ නෝරපුල්ලේ ගියාම ඒක රහස් වෙන්න මම පුළුවන් දෙන්නේ. ඒකද frequency නේද? හිමින් කතා කරන frequency එක අඩු වෙනකොට wavelength එක large නේ. ඒක හිමින් කතා කරනකොට ඇහෙනවා. Right? Have you light waves here? Diffract in a light wave diffract on when I think there was over the Baran. Every diffract. It's a large gaps of diffract in it. Now, light to diffract, 2 gaps. You're diffracting grading scale. Micrometer, millimeter, with gaps. What is that? Here, there are absolutely gradings. We can see diffracted patterns of light using the gratings. But we can diffract the light from very small gaps or very small holes, right? Not such like this gap between the size of the even that. What is that kind of way? Like there's not a window, we can see it. With different, right? So now a band එකක් කියමුකෝ බෑන්ඩ් එකක් කියමුද බෑන්ඩ් එක ප්ලේ කරන්න යනකොට බෙන්ඩ් එකකින් යනවා බෑන්ඩ් එක වෙන්නේ නේද අන්තිමට කොහොමද පුළුවන් සවුන්ඩ් එක බලන්න අන්තිමට මෙහෙ බෑන්ඩ් එක ඇතුලේ ඉන්නවා but you can බෙන්ඩ් එකකින් යනවා ඇතුලේ යනවා වයිඩ් බෙන්ඩ් එකකින් but you can hear the sound of the bass එක එනවා නේද උසන පොඩි ඒවා හෙන්නේ bass එක එනවා ගොඩක් යනවා ඇයි bass කියන්නේ it is low frequency wavelength is high. Right? And sound waves ටික ඒ bass එකේ waves ටික bend එකේ bend වෙලා හොඳට එන ගොඩක් වෙලා යනවා. That's there. Right? So that is the beauty of diffraction. Right? So මෙච්චර දැනගන්න ඕනේ. Diffraction is the phenomena of the wave passing the edge, it bends and spread out. So when a wave goes through a narrow hole or aperture, also wave will spread out and keep the wavelength similar and goes out, right? And also the size of the obstacle or aperture will decide the if the diffraction is well or not. Diffraction happens very well or not. If the size of the aperture is less than the wavelength of the wave, diffraction is well, right? And also the if the size of the aperture is very large compared with lambda, wave will not get different, right? Topically, yeah. So we get common diffraction calculations in a formulas, but no calculations are there, right? So diffraction. But yeah, diffraction is the phenomenon. Diffraction is the phenomenon. Diffraction is the phenomenon of bending. Phenomenon of bending. Phenomenon of bending. Waves around edges. Waves around the edges. Waves around the edges of an obstacle. O, obstacles O, as they pass through an aperture. AP, APERTURE, aperture. TURE. APERTURE, aperture. Within bracket, a small hole or a narrow hole. Small hole, right? Aperture. Wave is spread out. Wave is spread out. Right. The diffraction is decided by the size of the diffraction is decided by the size of the aperture of obstacle. Size of the aperture of obstacle. Within bracket simple A. And the wavelength of the wave. The wavelength lambda of the wave. Right. So you can draw these wave forms. Right. First make only to this along. This is the first figure. Yeah. Right? Finished? Right. So try to go in these two figures, the wavelength. These two figures are same wavelengths. Same wave, but the size of the aperture is different. Here it is a narrow one, here is a wider aperture. Okay. Right. Now, polarization of waves. Polarization of waves. Polarization of waves. So what is polarization? Polarization is the phenomena that only transverse waves can show. Right? Only transverse waves can polarize. Why is that? Polarization means, right? So when a transverse wave vibrates in different planes, right? So these are the vibration. Suppose these are the oscillating planes of the transverse wave. And wave the planes are oscillated. Right? So this is unpolarized wave. This is unpolarized. And polarized means we restrict the oscillation of this transverse wave to a single plane, right? From this situation to here. Right? Here we have the transverse wave oscillating in various directions or various planes. Polarization is the method of phenomena that we restrict the oscillation plane of the transverse wave to a single plane. Right? So suppose this is the electromagnetic wave. For example, it is a light wave. So light wave has a various planes it can oscillate. So if we limited that oscillated planes into one plane, what happens to its energy or intensity? Intensity decreases. Energy decreases. Suppose you have a string there, right? So we are oscillating this string, then we will oscillate, right? Then polarization means we limited that oscillation planes of the string to only one plane, right? So that will minimize the that will reduce the kinetic energy of the. That means the energy of the wave reduces. due to polarization, intensity and energy reduces. So you can't polarize the longitudinal waves. That's why I told this is only valid for the transverse waves. Why is that? Why you can't polarize the longitudinal waves? Look at that. In longitudinal waves, particles move this line. Only one. Direction is parallel. So you can't polarize sound waves. Right? You can polarize light waves. Because light waves are transverse. Sound waves are what they are longitudinal waves. Right? So you can demonstrate the polarization of mechanical waves by using a small activity. Suppose we have made a slit using cardboard sheet. We make a slit on a cardboard sheet. It's a narrow vertical slit. Yeah. Right. So we have a string. Right. The string has now the string is going through this slit. So now we vibrate this string at this end to various directions. Right? So we vibrate the string on these directions. Right? So that will produce transverse waves in various planes. And we have transverse waves over. And also there may be a transverse wave like this plane. Right? Now what are the problem? But what can you say? What can you see after the string passing through this vertical slit? The vibrations of waves at which plane will transmit through this slit? All the waves have make up now only oscillation in vertical direction that will pass through this slit, right? And the horizontal vibrations, they can't pass through this vertical slit, right? So the slit take a vertical and we have the oscillation for a vertical direction oscillation like me what is the right? Only the waves which vibrates in the plane parallel to the where the slit is at goes through the pass through this slit, right? Only. So if we have another slit which is a horizontal one, now what can you observe? If this end of the string is passing through horizontal slit, after you pass this slit, so there's no vibration go further, right? Vertical leg, so totally polarized. Polarized cannot totally vibration. Right? Energy totally. Right? So this is the process we call polarization. So what is the polarization? Polarization is the phenomenon that only transverse waves can show, and it is the it is the property of transverse wave that we can restrict the oscillating planes of the transverse wave to only a single plane. Right? If the wave is oscillating in various planes, you can restrict the oscillation of the transverse wave to a plane like this. Right? So that is polarization. So we use polarization to like a 3D films or 3D glasses use करना है intense gravitation or night vision or drive करने में use करना glasses वाला polarization use करना right but a 3D cameras वाला polarization के लिए use करना to reduce the intensity and sometimes you can form 3D image using this polarization holograms like those things we can use polarization right so only we need this qualitative things about polarization. कुछ calculation से कुछ कराने लिखा what is polarization की तरह भाई जानेगा तो clear polarization is a phenomenon polarization of waves polarization is a phenomenon which unique to transverse waves. It is a process. It is a process which the oscillating planes of transverse wave are restricted to one plane or to a single plane. Perpendicular to the direction of wave propagation In chemistry, I think you also mention about polarization. Polarized light. No? And you know, they were so. You know, structures of the get some I should have no, I should have said. I think I So you can draw this. deep and moment finish. Chromatiano oscillations parallel to the plane of the oscillations parallel to the perpendicular to the plane of the sheet on the transmit element of the sheet plane perpendicular direction oscillations is right making area. With that, I'm taking on. Go over there on a green. I get a sheet take a theatre, the sheet take making area on a sheet take a plane, and I may plane take a perpendicular plane, right? Right. Alright. Next topic is speed of longitudinal waves. Speed of longitudinal waves. Properties you are wave properties you are. Speed of longitudinal waves in different mediums. Speed of longitudinal waves in different mediums. Right. So if you remember, a longitudinal wave is a one that transmits by oscillating particles direction parallel to the wave properties. Right? In that case, they form compressions and rarefaction. Particles get compressed and released. Right? So in order to travel a longitudinal wave in a medium, it must require some qualities, depends on the medium. Right? So particle in the medium should have the ability to contract and release. That depends on the elasticity of the medium. Or you can say modulus of elasticity of that medium. Right? We have contractile. That elastic property, it depends on the elastic property of the medium. So the speed of the longitudinal wave in the medium depends on the elastic modulus of the medium. That we represent as capital E, elastic modulus. Elastic modulus of the medium. And also to the speed of the longitudinal wave in a medium depends on the how much density medium. If the medium has more particles, that has some effect on it. Right? Particles would have effect. Right? So if the medium has more particles, the density of particle is right. So the number of particles in medium depends on the density of the medium. Right. So therefore, density is another factor that decides the speed of a longitudinal wave in a medium. So these are the two factors: density and elastic modulus. Right? So speed of a longitudinal wave depends on these two quantities. Right? This is the relationship. Speed of a longitudinal wave in any medium is given by square root of E over O, elastic modulus of the medium divided by density of the medium, and get the square root. So this is the expression for the speed of the longitudinal wave in any medium. So this is known as Newton's equation. Newton's equation for speed of longitudinal waves. Newton's equation. Right. So what are the mediums that we can look after? Right. There are three states of matter. That depends on the nature of the state of the medium. I will come to that. Right. So what are the mediums that you can have? You can consider solid medium. Solid. For solid mediums, the elastic modulus is known as Young's modulus. Young's modulus. E equal to y. That your y is Young's modulus. Young's modulus. Young's modulus. Right? So you can write the expression again by replacing this elastic modulus from Young's modulus. So you can write it as y divided by rho square root. For solid mediums, the speed of longitudinal wave is given by square root of the Young's modulus of the medium divided by density of the medium. Right? Then, for fluids, it means for gases or liquids. Liquids and gases. Right? So for liquids or gases, this elastic modulus is known as bulk modulus. We say it as a bulk modulus. Bulk modulus here like that. Bulk modulus. This is bulk modulus. So the speed of longitudinal wave in a fluid medium is given by bulk modulus divided by density of the medium. The only thing is that the elastic modulus is changed with the nature of the medium. If it is a solid, elastic modulus is known as Young's modulus. If it is a fluid, liquid or gas, elastic modulus is bulk because these fluids have bulk properties. Fluids have bulk properties. If we apply pressure, volume change. Right? So if we apply force to a metal wire or something, it will get the so that will exert tensile stress and tensile strain. So that depends on the Young's modulus. So therefore, for solid mediums, we use Young's modulus as the elastic modulus. Right? The main equations are right? Bulk modulus right? The longitudinal wave speed, the longitudinal wave speed in a medium, the longitudinal wave speed in a medium depends on elastic properties and the density of the medium. The relationship the relationship between speed of the longitudinal wave, speeds of the longitudinal waves within bracket simple b, and elastic modulus within bracket capital E, and the density rho, density symbol is rho, is given in below. Right, so V equals square root of E over rho. Square root of E over rho. E is elastic modulus, rho is yes. Right. What is topic capture recurrence speed of the longitudinal wave in a solid medium. Speed of the longitudinal wave in a solid medium. Mark the topic speed of a longitudinal wave in a solid medium. Right. And then for solid mediums, elastic modulus is considered as Young's modulus. Elastic modulus is considered as Young's modulus. Right. So here elastic modulus is now Young's modulus. Normally we use Y. Sometimes we use capital E also, right? Young's modulus capital E use karna, Y use karna. In some books they use this symbol also. The මේවත් කියන බලා නැත්නම් මේක limit වෙන්න බා. Young's modulus එක මෙන්න මෙහෙම psi. ඔන්න ඔය symbol එකක් use කරනවා. Some books they use Y, E ඒ ඔක්කොම තියෙනවා. එම depend එකම ඉතින් නැති වෙන්න පුළුවන්. But here මෙතන එන quantity එක physical quantity එක should be Young's modulus. So E equals Y. We use Y. Or use current Y is Young's modulus. So here's the expression. V equals square root of Y over rho. Oh, speed එක දෙලා elastic modulus ගන්න පුළුවන් යා අපි properties of matter වලින් කතා කරනවා elastic modulus ගන්න. Yeah, it has unit. Elastic modulus it is the same unit as a pressure. This Young's modulus unit is pressure. Newtons per square meters or Pascal. The elastic modulus එක unit එක කියන්නේ Pascal. Right? Alright. Next topic is speed of the longitudinal waves in liquids and gases. Speed longitudinal waves in liquids and gases. Liquids and gases. For liquids and gases, elastic modulus is bulk modulus. Elastic modulus is bulk modulus. Therefore, speed of longitudinal waves, in liquids and gases is given by here like this: E equals V over O. Since sound is a longitudinal wave, the most famous longitudinal wave is sound wave, right? So these expressions also valid for sound waves. As sound waves are very clear. Like write an example question. Write an example question. Find the speed of the sound waves in steel. Like density of the steel, density of the steel, density of the steel 8,000. Density of the steel is 8,000 kilograms per cubic meter. And Young's modulus for steel is 2 times 10 to the power 11 newtons per square meters. Like this. And what is the value? 5,000. 5,000. Oh. 7. This is very simple one. V equals y divided by 2. Square of y is 2 times 10 to the power 11. 8,000 කියන්නේ මෙහෙමනේ. 1 එතකොට 4 එනවා. ඒකට ගියාම 3 එක minus 3 වෙනවා. 10 to the power 8 is remain divided by 2. අතෝලේ අතට පොයි. So මේක square root එක ගත්තාම 10,000 divided by 2. 5,000. Right. Right. Second question. Find the speed of sound in. Find the speed of sound in water. Density of water is 1,000. Density of water is 1,000. And the bulk modulus of water. Bulk modulus of water 2.2 gigapascal. Bulk modulus of water 2.2 gigapascal. Gigapascal. Right? Well, meters per second. Sorry. 50 meters per second. What? Meters? Is it 1,480? Huh? 1,480 maybe? 3. 1480. So that is less than the speed of sound in steam. Still not to 1000. Find the speed of sound in air. Find the speed of sound in air. Find the speed of sound in air. Density of the air. Density of the air equal 1.3 kgm minus 3. Bulk modulus of air. Bulk modulus of the air 1.4 the 1.4 times 10 power 5 bulk modulus. That's it. Modulus in Pascal. Right? Value 2000. 300 or 328.17. Right. And so now actually then हमें अभी point पे जाएंगे. Actually, initially, so now we're going to see the speed of sound in air. The expression is the speed of sound in air. Speed of sound in air. Speed of sound in air. Right? So sound waves are longitudinal waves. So speed of sound in air is also given by the expression V equals bulk modulus of the air divided by density of the air and get the square root. Right? So initially they thought this bulk modulus of the air is equal to the pressure of the air. Right? Newton did this. He assumed the when sound wave propagates in air, right, it is an isothermal process. Isothermal, the temperature remains constant. Right? From that assumption, by that assumption, he states that the bulk modulus of the air depends on the pressure. It is equal to pressure. But lately, it was discovered it is a wrong assumption. Actually, the speed of when a sound wave travels in air medium, right? That process is not isothermal one. It is adiabatic. අපි process ගැන කතා කරනවා equally ඒකෙදි it is not isothermal one. ඒකෙන් temperature constant වෙන්නේ නැහැ sound wave වලට යනකොට. Constant වෙන්නේ heat energy. Particles වල heat energy එක තවකට transfer වෙන්න time එක නැති වෙනවා. Right? So if a process the process where the energies remain constant, there's no energy exchange between the system and the surrounding. Those processes are called as adiabatic process. Right? When a process happening, the temperature of the system is remain constant. Those processes are known as isothermal. Initially, Newton thought the propagation of sound waves in air is isothermal process. Right? Then he introduced the expression V equals P over rho square root by assuming this process is isothermal. Right? But lately, Laplace gave a correction to that. Laplace, Simon Laplace, scientist, he gave a correction to this. Right? He thought when the sound wave propagates in a air medium, the process is adiabatic process. Therefore, bulk modulus is given by this expression gamma times p. Gamma times p. Not only the pressure is the factor that decides the speed. It also involves another quantity, which is gamma. Right? I will calculate this quantity after mentioning the expression. So therefore, speed of sound in air is given by now this expression gamma p over rho square root. Square root of the gamma p over rho is the correct equation which gives the speed of sound in air. Right? So nowadays we use this expression to find the speed of sound in air. Right? We also use this expression when we find the speed of ultrasonic waves, ultrasound waves. Right? We use this when determine the speed of the ultrasound. In normal sound, the audible sound, this is the expression we use. Right? Make a mention මේක අපි use කරන ultrasound waves වලට අපි normally කතා කරන අපේ audible sound waves වලට use කරන this expression. Right? So it is isothermal process. Therefore, we use gamma p as the bulk modulus. Right? Gamma p use කරන්නේ. Right? What is this gamma? This gamma is the ratio of two main specific heat capacities of a gas. This gamma is the ratio of two main specific heat capacities of gas. Right? The gas has two main specific heat capacities. What are those two main heat capacities? One is Cp. Cp is the specific heat capacity at constant pressure. Constant pressure. Specific heat capacity at constant pressure. Then Cv is the specific heat capacity at constant volume. Constant volume. These are the two main heat capacities of a gas. So gamma is defined as Cp over Cv. Gamma is Cp over Cv, which means specific heat capacity of the gas at constant pressure divided by specific heat capacity of a gas at constant volume. Right? So gamma has no units because these two quantities are specific heat capacities. They have same units. So gamma is unitless. And gamma is also known as atomicity. Atomicity. I think in chemistry you will study this. वो chemistry का नाम करना थी gas law से मतलब आता है ना process chemical process से करना होता है isothermal adiabatic isobaric okay this is known as atomicity, right? So this gamma is depends on number of atoms in a gas molecule. If it is a diatomic molecule, gamma has a certain value. If it is a monatomic one, it has a value. Right? For diatomic gases like hydrogen, nitrogen, and oxygen, for diatomic gases, the gamma value is nearly 1.4. For the monatomic gases like helium, neon, this gamma value is nearly 1.67. Diatomic gas also one. CO2. The gamma value is nearly 1.33. No need to remember these values. They will give it. They will provide it. Arithmetic values there. But normally, diatomic 1.4. Yeah, you want to give it. Right. So gamma has that value. Normally, normal air, which means majority of the air consists the greater percentage of air consists N2 and nearly 20% is O2. So normally, in normal air, the gamma value is equal to 1.4. We take gamma as 1.4 for the normal air. Right? But in diatomic gases, the combination again is 1.4 to N. Right. So what is P here? P is the pressure of the gas. P is pressure. And rho is density. Density of the gas. Right. So this is the expression. So what is this expression used to? Used for? To determine the speed of sound in air. Right? Bulk modulus is given by gamma P. Right? අපි කිව්වා මේ equation එක මෙතෙන් ආව ඇයි කියලා. මේ equation එක ඒගොල්ලෝ දුන්නේ they thought the process is isothermal. When the sound wave propagates in the medium, that process is isothermal. That means the temperature of the particle or system remains constant when the wave propagates. That was proved wrong lately. So therefore, Laplace gave a correction to that, and he stated that that process is not isothermal; it is an adiabatic one. In adiabatic process, we use this symbol gamma. Processor लोगों ने कहा था कि gamma की निकाल क्या नाम है? right? So in detail they are in there. So therefore bulk produce is given by gamma times pressure. Right. So we replace B from gamma times P, then the equation transform into V equal square root of gamma over. That's it. Right? Topic again. Speed of sound in air. Speed of sound in air. Speed of sound in air. Right? Sound is a longitudinal. Sound is a longitudinal mechanical wave that requires a medium to propagation. Speed of a sound wave in a gas depends on the elastic and inertial. Elastic and inertial. How's inertial? I-N-E-R-T-I-A, inertial. Property is of the medium. Next sentence. For a gas medium, speed of sound. Sorry, for gas medium. The bulk modulus. For the medium is given by V equals gamma times P. V equals gamma times P. Within brackets there, because process of sound wave propagation is a adiabatic process. Adiabatic process. Hence, speed of the sound in air or a gas is given by V equals square root of gamma P over O. V equals square root of gamma P over O. V equals square root of gamma V over rho. Where the gamma is the ratio of two main specific heat capacities of a gas. Gamma is the ratio of two main heat capacities. Right? These are the two main heat capacities. Right. These are two main heat capacities, Cp and Cv. Cp and Cv. And again, gamma is the ratio of two main specific heat capacities of a gas. It is also known as atomicity. When the heat capacity is mentioned, gamma expression standing equation gamma is Cp over Cv. Cp is this. Cv is gamma is Cp over Cv. Value of the gamma, value of the gamma, value of the gamma depends on the value of the gamma depends on the number of atoms in the gas molecule in a gas molecule right. For monatomic gases for monatomic mechanical count, this is monatomic. Diatomic. So that is right. Here P is pressure of the gas or density of the gas. right? Write an example. Find the speed of sound in air. Find the speed of sound in air. Example. Find the speed of sound in air at standard temperature and pressure. Standard temperature and pressure. STP. Standard temperature and pressure. Density of the air is 1.29 kgm minus 1.2. So what is the standard temperature of in physics? Chemistry or chemistry? 25. Physics or 06. Kelvin 273. 06. What is standard pressure? 180 1.013 times 10 to the power 50, 10 to the power 5 pascals. Standard pressure is value of the standard pressure is 1.013 times 10 to the power 5 pascals. Standard temperature 273 kelvins. Remember in this here on remember when you substitute for temperature in these expressions, you need to convert the given Celsius temperatures to Kelvin, right? All the temperatures must be as substituting Kelvins, right? इसे मिला तो अपनी Celsius cooling temperature में physics वाली main equation तो अपनी substitute करना है हम लोग क्या है का Kelvin temperature हमारी डाल दो, yes. What is it? Standard? Normal. The normal means 27. For example, room temperature. Room temperature is the right. Find it. What is the value? No. Use log tables. What is the value for gamma? You need to assume the AI is diatomic one. So gamma is 1.4. 8 gamma is 1.4. Gamma is 1.4. Yes. 1.01. So here you will not require the temperature, standard temperature, but you will be value 331. So answer will be 331 meters per second. 331. Alright. Answer guys. How? Yes. All right. Right then, all right. So now we are going to see the relationship between temperature and the speed of sound in air. So V equals gamma P over rho square root. Right? So we assume air is ideal. Air is an ideal gas, right? So assuming air is ideal gas, so you can apply the ideal gas equation. So what is ideal gas equation? Using ideal gas equation. So what is ideal gas equation? PV equals N RT. So N is the number of moles. So number of moles N equals mass of the mass over molar mass. right? Right. So P V for this N, instead of N we write simple M over capital M, R T. Then divide both sides from capital V, M R T divided by V into M. So V cancels. P equals. So what is M over V? Density of the gas. RT over M. So divide both sides from rho. So we have a ratio of P over rho. Pressure divided by density is equal to RT over M. RT over M. Now the equation is gamma P over rho. So we have a P over rho term here. P over rho term. So V equal gamma P over rho. Right? Instead of P over rho, I wrote this RT over M. So gamma RT divided by M. Yeah. So P over rho වෙනකොට අපි use කරනවා මෙන්න මෙයා RT over M use කරලා expression එකක් ගන්න. Right? So what is R here? R is the universal gas constant, where R is universal gas constant. The value of R is equal to 8.314 joules per mole per Kelvin. Right. So what is capital M? Molar mass. So most of the occasions, molar mass is given as a gram per mole value. Right? Here you need to substitute that molar mass and convert it to kilograms. Grams, kilograms, color within the right? Temperature should be, it must be absolute temperature, right? So this is the expression. Temperature dependency of speed of sound in air, right? So for a given gas, gamma R and M this gamma R and M are constant. For a given gas, gamma is a constant. If it is a dynamic form, gamma is a fixed. R is a fixed value. M also fixed value, right? So therefore, all these terms are constants. So V directly proportional to the square root of temperature. That is the relation between temperature and the speed of sound in air. Speed of sound in air directly proportional to the square root of the absolute temperature of the air. So if you double the temperature, what is the factor that speed of sound in air increased? By root 2. If you double the temperature double now root 2 වලින් තමයි ඒක වැඩි වෙන්නේ. හරි? root 2 වලින් වැඩි වෙන්නේ. Right? In order to double the speed of the sound in air, right? What is the factor you need to increase the temperature? 4 by 4. අතනොබේ වැඩි කරලා speed එක දෙපිටින් වැඩි. වැඩිද? Right. Topic clear. Relationship between relationship between temperature and speed of sound in air. Right. So you can start from here. V equals MRP over O, right? Using ideal gas equation. Come up to here. Then get the expression. Mathematical, yeah. Yes. Are you finished? Up there? Here point ಹಾಕಿದರ speed of sound in air, speed of sound in air, speed of sound in air is directly proportional to the speed of sound in air, directly proportional to the square root of the absolute temperature right. So now write this V proportional to square root of absolute temperature right. Another thing, right? Suppose like for a given gas, a certain gas, speed of sound in two temperatures, two situations. The first one, when the temperature is T1, suppose the speed of sound in air is V1. At temperature T2, speed of sound is V2. So we can get a relationship between V1, V2 and T1, T2. Right? As you can see there, speed of sound is directly proportional to the square root of the absolute temperature, which means V equals a constant time times square root of T. But in the first case, V1 must be equal constant times square root of T1. Let us take it as equation 1. For the second occasion, V2 is equal K square root of T2. Right. Equation 1 over equation 2. V1 divided by V2. Right. We can cancel this constant K. Then finally, we have an expression relating to V1 and V2 with the absolute temperatures T1 and T2. Here, final expression. The එකම gas එක temperatures දෙකකදී speed of sound in air ratio එක ගන්න ඕනේ. Right? So if the temperature is given in Celsius, how you get the absolute temperature? If the temperatures are given in Celsius, suppose the temperatures are θ1 Celsius and the other one is θ2 Celsius. So then the expression is V1 over V2 equals, right? If the temperature is θ1, so you can write T1 as 273 plus θ1. And also, temperature capital T2 is 273 plus θ2. Then the expression is 273 plus θ1 divided by 273 plus θ2 square root. When the temperatures are given in Celsius, you can use this. Right? The equation is good up for the make resonance tubes expression. Temperature speed of sound in air. Our temperature speed. So we equation I use right. So this is the equation we use for get the relationship between the speed of sound in air in two different temperatures for a given particular gas. If a gas के temperatures देकर the speeds run. Correct? So you can extend the one, right? Suppose suppose speed of sound. Suppose speed of sound in a certain gas. At absolute temperatures, capital T1 and T2, capital T1 and T2 are V1, V2, V1, V2 respectively. Capital V1, V2 respectively. Like this. Now write down this. Now make it vertical. Yes. Sorry. T. Direct proportional T. What is T there? Difference. Yeah, good. Can I like done that? I remove turn slide and I've done this later or 626, 646. First, 1 hour के लिए तो काम करता है मैं क्वेश्चंस के अंदर जो सब फिक्स हो जाएगा right someone at 7:30 वगैरह मैंने काम lesson के 7:30 or 7:45 lesson के after that we move on to the optics. Okay. Yes. What do we have? Hey, she got it. Either. Well, and they were taken in both and in a census Venus. Make a wedding. Audio And let's see how the speed of sound in air depends on pressure, right? The speed of sound in air, how the speed of sound in air depend on the pressure. What can you say? Dependency with pressure. Pressure increase. Sorry. Increase. So by looking at this expression, V equals gamma P divided by rho and square root. And also, to remember, earlier we obtained this ratio P over rho is RP over M, right? So this is a important thing here. So P over rho, right? So R and M are constant, right? R is a universal constant. M is constant to given gas, right? Given gas. So if the yeah, part of the sorry. So if the temperature is constant, look at here. If the P is constant, this whole term is a constant. That means P over rho is constant. When the temperature is constant, when you increase pressure, what happens? Density also increase. If you decrease pressure, density decrease, and it maintains that P over rho ratio as a constant. That means when the temperature is constant, if the temperature is constant, speed of sound in air does not depend on the pressure. It is independent from the pressure. Right? When the T is constant, temperature is constant, that means P over rho ratio is constant. Hey, we are not rolling. Right. මේ temperature එක වෙනස් වෙන්නේ නැත්නම් temperature එක constant නම් මේ ratio එක constant වෙනවා. මොකද pressure එක වැඩි කරොත් density වැඩි වෙනවා. Ratio එක constant. That means if the temperature is constant, V does not depend on the pressure. Right? Remember that. When the temperature is constant, speed of sound in air is independent from the pressure of the air. Like it. Dependency with pressure, of pressure. Right? Speed of sound, yeah. Dependency of pressure. Dependency of pressure. Right under it. When the temperature is constant, when the temperature capital T is constant, when the temperature capital T is constant, P over rho equals RT over M. P over rho equals RT over M. Therefore, P over rho is constant. P over rho is constant. Right? P over rho is constant. Hence, speed of sound in air. Hence, speed of sound in air is independent from the pressure. Is independent by the pressure. From the pressure. Speed of sound in air independent from the pressure. When temperature is constant. Temperature is constant. Then dependency with what? Say humidity. Humidity. So what is humidity means? What is humidity? Huh? They already know this. Only the maintaining negative equation. Right. Right. So, what is the meaning of humidity? What is the term humidity stands for? Humidity. Amount of moisture in air. It is a measure of amount of moisture in air. If the amount of moisture is high, right, humidity is high, right? So, how is effect to the speed of sound in air? How the moisture content in air affects to the speed of sound in air? Have you argued that? Right? Como da big argue करना? P equals gamma R T O M square root. So what affect the humidity? Does humidity affect the gamma? No, it is depends on the number of molecules in the atom. Humidity affect the universal gas constant? No. So universal constant. So the temperature? No. So what affect? To the molar mass, mean molar mass of the air. What happens if the humidity is high? To the mean molar mass of the air. So what is the what is the molar mass of the dry air? Dry air, the majority of air consists of nitrogen. So what is the molar mass of the nitrogen? 20. So the mean molar mass of the dry air is approximately 28 grams per mole. What is the molar mass of water vapor? 80. So when the humidity is high, that means the amount of water vapor in the air, given volume of air is high. So that will affect. How that will affect? If the moisture content is high, means the mean molar mass of the air reduces. Dry air air water vapor ඔක්කොම nitrogen නම් තියෙන්නේ. නැත්නම් ඔක්කොම dry air particles නම් තියෙන්නේ is 28. දැන් මේ volume එක ඇතුලේ water vapor replace වුණොත් එහෙම 28 තිබ්බ molecule එකක් replace කරලා 18 වෙන්නේ. ඒක mix වුණාට පස්සේ එන mean molar mass is less than 28. Right? So if the moisture content is high in the air, that will affect to reduce the mean molar mass of the dry air. Right? It is a value less than 28 now, if the humidity is high. So that means when the molar mass is decreases, molar mass is decreasing, what happens in sound speed of sound in air? It increases. If the humidity is high, mean molar mass of the air is reduces. Right? That will affect as an increase of speed of sound in air. Molar mass right? This molar mass is inversely proportional to the speed of sound, inversely proportional to the square root of the molar mass. When the mean molar mass is decreases, speed of sound in air increases. Right? Yeah. Yeah. When humidity is high, when humidity is high, when the humidity is high, this is the topic. Dependency with humidity. If the humidity is high, mean molar mass of the air decreases. Mean molar mass of the air decreases. Therefore, Therefore, speed of sound in air increases. Right. So you can write down this. So V inversely proportionally square root of molar mass right? When the humidity is high, mean molar mass is less than the dry mean molar mass of dry air, which is 20 grams per mole. So this will affect as an increase of speed of sound in air. Right. So you take that. Turn to page number 50. Sorry, page number 5, question number 50. Right, waves tutor, waves and vibrations. Yes. Question number 50. You can skip part 1 of the question. Do only part 2 and 3. Question number 15. Do the questions part, the part 2 and 3. Question number 15, page number 5. How you solve the second question? Temperature is given there, right? Temperature and pressure. Is the speed of sound in depends on the pressure. You can forget the pressure and use the V equals square root of gamma T over the equation. Fine. What is molar mass? Molar mass? Which one? Part B or C? Part B. The speed of sound in air was found 320 meters a second at an atmospheric pressure 72 mercury and temperature of 7. What is the speed of sound in air at atmospheric pressure of 76 mercury and temperature? So here you do not need to use this one. Earlier we took an expression, the relation with the two speed of sound in air in two different temperatures. We can use this one. We have given the temperatures and one speed given there. Use this equation. Making a pressure not relevant here. Pressure is not relevant. Speed of sound is 320 is 320 when the temperature is 7. And which means in Kelvin it is 280. Temperature 27 is in Kelvin 300. So V2 equals 320 times 300 divided by 280 square root. What the value again? Right, the example number of calculators. Properties of matter and radiation, gravitational fields, इसमें भी तो सब simplification ने करेगा use करेगा. Another second one. Second question again answers. See, what should be the temperature for the speed of sound in hydrogen gas to be same as the speed of sound produced in oxygen in 727. 727 neither. What should be the temperature for sound in hydrogen? Let's take the temperature as T. Temperature of the O2 is 727. Gamma, value of gamma is same. R is same for both. So what is the M value? Molar mass for hydrogen? 2 grams per mole. For O2? 32. 32. Both the speeds are same. VH2 and VO2 same. Right? So expression is V equals gamma RT over M square root. Right. So VH2 is gamma R temperature is needed to be found. Temperature is I can know it. Molar mass of hydrogen. So here no need to convert it to the kilograms. Both the molar we can write both the molar masses as grams or moles. Right. So this is the VH2 and VO2 is gamma is same, R is same temperature 727 at 273 to it to get the Kelvin temperature which is 1000. Molar mass of the O2 is 32. Now the question says the both the speeds are same. Then equal to equations. Equal term. Gamma RT over 2 square root equals gamma R 1000 over 32. Gamma R cancels. Square root item so T equals 1000 into 2 divided by 32. 1000 divided by 16. 16 or 96. 40 over the 62.5 kelvins. 62.5 kelvins. Like take the MCQ. MCQ. I mark these questions. Question number 2 and 3. Question question number 2, 3, and question number 10. Twelve, 10, 12, 10, 12, and 16. Thank you. The question. It's 5. 28 and 29. 28, 29. 28, 29. MCQ tutorial. Yeah, what is the wavelength of a 512 knot in air at this temperature? That's all. Value pick up. 27. You know the speed. Now you have taken the speed here. So use V equals f lambda. So what is the value of V2 here? And the V2 value is here. You can run that. What can I kill on? 0.647. This one, V2. It should be 321. 331.2. The frequency is 512. Level is lambda.